Hi, I'm Dr. Melanie Hartman. I'm a Senior Research Associate at the Natural Resource Ecology Laboratory here at Colorado State University. And I'm going to be a guest lecturer for the next two class periods and talking about ecosystem modeling and in particular the century and descent ecosystem models. I've been at NREL for about 28 years and worked with a number of ecosystem models and helped develop both the century and descent models during that time. So over the next two classes, I've divided the lectures into four different parts. And the first part in this recording is going to discuss common terms in ecosystem modeling, some simple models of plant growth and soil organic matter decomposition, example temperature and soil moisture effects on the rates of decomposition in plant growth, and about ecosystem models in general. What are they exactly? In part two, I'll be talking in more detail about the century and the daily century ecosystem models. And when I say descent, that just means daily century. And some emerging ideas about soil organic matter dynamics in models that are currently being developed. Part three, we'll look at some descent results and talk in detail about carbon and nitrogen cycling feedbacks and manage agroecosystems. And then in part four, we'll be computing net greenhouse gas emissions, CO2 equivalents, and looking at some performance metrics for evaluating model results. So in particular, part three and part four will be really valuable to your homework assignment this week. But there's also some references for you. There's a chapter on the century model by Parton et al. 1994, and when you read that, you can just focus on the initial part of the chapter that describes the model and process descriptions, and you can skip over all the gritty details of the equations and figures. And for your homework, we'll be looking at some model results that were actually used for a publication that I published in 2011, and a reference, Jossen and Hauberger, which will discuss performance metrics that are used for ecosystem models and other types of models. So part one, concepts in ecosystem modeling, modeling plant growth and soil organic matter dynamics. So here's a diagram of some dynamics in ecosystems that we care about in ecosystem models, and all of these terms are defined in the next slide, so you don't have to remember everything that I said exactly. So think of a tree growing and tree dropping litter, and that litter becoming soil organic matter, and then there's some net amount of carbon gained by the ecosystem or lost by the ecosystem when these processes are occurring. So GPP, gross primary production, is photosynthesis, the net amount of carbon that a plant fixes. But not all of that carbon actually goes to the growth of the plant, which is net primary production, or NPP. Some of that carbon is lost through growth and maintenance respiration, and that's known as autotrophic respiration, and that can occur from any plant part. And then when microbes decompose soil organic matter, it's known as heterotrophic respiration, and that also releases some CO2 back into the atmosphere. So net ecosystem exchange, NEE, is the sum of all respiration fluxes minus GPP. So NEE is negative when the amount of carbon fixed is greater than the amount lost by respiration. And that's desirable from a greenhouse gas standpoint when we want to reduce greenhouse gases in the atmosphere. So just to review these terms again, GPP, gross primary production or photosynthesis, net carbon fixed by the plant, but then some of that carbon fixed is lost through autotrophic respiration, abbreviated R sub A. Net primary production is the difference between GPP and autotrophic respiration. Heterotrophic respiration is respiration by soil microbes. Net ecosystem production is just the opposite in sign of net ecosystem exchange. Net ecosystem production is GPP minus the two respiration fluxes in the ecosystem. This NEP is positive when the ecosystem gains carbon. It's negative when the ecosystem loses carbon. And so this is from the perspective of the land. A positive value is a gain of carbon on the land. Net ecosystem exchange is just the opposite of NEP. It's negative when the ecosystem has a net gain of carbon. That means the land is a sink. It's from the perspective of the atmosphere. So when we're concerned about greenhouse gases building in the atmosphere, we want NE to be negative. That means there's a net reduction in greenhouse gases in the atmosphere. And another way to look at this, some of the same terms that we've already gone over. In terrestrial carbon cycling, we have a plant that's taking up carbon, fixing carbon through photosynthesis, but some of that carbon that's fixed is lost through autotrophic respiration, and what actually goes into the biomass of the plant is net primary production, or NPP. Heterotrophic respiration is loss of carbon from the soil, and when you add up all those terms, you get NEE, the net ecosystem exchange, which is the sum of the two respiration fluxes minus the GPP. And we usually represent just the carbon part of CO2 in the ecosystem, but when we say heterotrophic respiration or autotrophic respiration, even though it is really CO2, the models are just representing the carbon portion of that CO2. So start off with a very simple two-pool model of an ecosystem. So a pool is storage of some quantity. In this case, we're going to look at storage of carbon in plants and carbon in soil organic matter. And fluxes are inputs and outputs from these pools. So in the case of the plant on the left side, there's this simple ecosystem model has a carbon pool for plants, just representing all the plants in the ecosystem and all the parts of that plant as is one big carbon pool. And then the carbon that goes into the plants is GPP, and carbon lost by the plants is autotrophic respiration. And plants can also lose biomass through death, and that plant litter gets transferred to a soil organic matter pool. So all the soil organic matter in the whole ecosystem, no matter what type of soil organic matter it is represented in this model as one big box of carbon. And then any decomposition of that soil organic matter is released as heterotrophic respiration. So again, net primary production is gross primary production minus autotrophic respiration, and the net gain by the ecosystem and EP is GPP minus the two respiration terms. There's a net gain of carbon in the ecosystem when NEP is positive. We'll look at a simple plant growth model. So just looking at the plant portion of the previous slide, but let's add some more detail to it. So again, we have one carbon pool that represents all the live biomass in the ecosystem. And the amount of carbon going into that live pool is the gross primary production. What's coming out of it is autotrophic respiration, and then the plant can also die and send that litter to another part of the ecosystem. GPP has some controls on it. We usually think of a plant as having a maximum GPP rate or a maximum photosynthetic rate. Some plants can fix more carbon than other plants. Some plants grow faster than other plants. So there's a maximum rate of GPP, and then there's some function of temperature, which is represented by F of T, some function of soil moisture or water, represented here as FW, and some function of solar radiation that's going to regulate GPP. And then in this simple model, there's just a fraction of what goes in comes out as autotrophic respiration. And these controls on the fluxes are represented as these hourglasses, and they can be one or more controls on the fluxes into and out of pools. And then this simple pool has just some constant death rate. Some fraction of the live carbon dies each day and becomes plant litter. So I've defined all these terms here on the left, the terms that I'm using in this simple model. And one thing to keep in mind is we'll be seeing a lot in the next few slides is these temperatures of, these functions of temperature and moisture and solar radiation can be like 0 to 1 factors. So when these values are 1, that means, like for instance, if the function of temperature is 1, that means that temperature is actually ideal for growth. When it's 0, there's no growth. When the function of moisture is 1, that means the soil moisture conditions are ideal for maximum growth. 0 is no growth, and numbers in between are somewhere in between no growth and maximum growth. So you can develop model equations from this simple diagram. The GPP is the maximum rate times the 0 to 1 multiplier of temperature times the 0 to 1 multiplier of soil moisture times the solar radiation function. The autotrophic respiration is a fraction of GPP. The net primary production is GPP minus autotrophic respiration. Plant litter produced is a fraction of live biomass, and the live biomass at time t plus 1 is what the live biomass was at time t plus what it gained through photosynthesis minus what it lost through autotrophic respiration minus what it lost from plant litter. Now here's an example of a simple soil organic matter model, just looking at two different soil organic matter pools. I'm not going to really define them in any particular way, it's just an example. So, but the idea is that plant litter enters one pool, pool A, that pool A decomposes and sends some carbon to pool B. And so the first order linear decay is just taking the amount of carbon that's in one pool, like pool A, multiplying it by some maximum rate of decomposition and then some temperature and moisture functions that can either allow decomposition to occur at its maximum rate or reduce it if temperature and moisture are not optimal for decomposition. Decomposition out of pool A is the sea flow, and some of the carbon that is decomposed from pool A will go to heterotrophic respiration, and the rest of it will go into pool B. And that's just this particular model. That's not how all models work. So the equations for this model is the amount of carbon that flows out of pool A is equal to the amount of carbon in pool A times a constant maximum rate of decomposition times these 0 to 1 multipliers of temperature and moisture, similar to what we saw in the plant model. Heterotrophic respiration is some fraction of this carbon flow out of pool A, and pool A at time t plus 1 is equal to what pool A was at time t, plus what it gained, plant litter, and what it lost, what the decomposition. Pool B at time t plus 1 is equal to what pool B was at time t plus what it gained, and it gained the difference between sea flow and heterotrophic respiration. So first order linear decay is a way to model soil organic matter decomposition, and it's linear because this Kmax, this maximum rate, is a constant, and it's first order because the amount of decomposition depends on the amount of carbon in the pool that is decomposing. I'm representing the units of these pools as grams carbon per meter squared because that's what the day and century models use. Other models might have slightly different units, but I'm going to try to be consistent so that all pools are grams of carbon per meter squared, and fluxes are grams of carbon per meter squared per day. And in the model, everything is just carbon. So look, for instance, at heterotrophic respiration. It's in this slide, I say it's the carbon in CO2. So CO2C means the amount of carbon in CO2. So it's really carbon that belongs in CO2, but in the model, it's just carbon. So let's take a look at some of these F of T's and F of W's I've been talking about, these controls. Soil organic matter decomposition. This is just one example, and this happens to be the one that the day sentence century model use. So all of these, or this temperature function, is a multiplier from 0 to 1, where 1 would represent a maximum decomposition based on temperature, and 0 would mean no decomposition. So the y, or the x-axis, is soil temperature. So you see this function starts off nearly 0 at minus 10 C, gradually increases as the soil temperature gets warmer, increases at a faster rate between 10 and 30 degrees C than it did when it was less than 10 degrees C, and then slows down again. So in this particular slide, this function is saying that at 50 degrees C, we would have temperature conditions in the soil that would allow for maximum decomposition. And this function just happens to be represented by this arctangent function. And you don't have to memorize that or anything. It's just one example. And I just wanted to put the equation down so you could see what it looks like. And the biological significance of this curve, I've sort of talked about it already, but the main thing to look at is like that the rate of decomposition would change as the soil temperature changes. So between 10 and 30 degrees C, every degree C increase, you get a much more rapid increase in this function than you would get if you increased temperature between minus 10 and 10 or between 30 and 50. The slopes of this function are much shallower at the lower temperatures and higher temperatures than in the middle. So that means the microbes, as represented in this model, respond quickly to temperature increases between 10 and 30 degrees Celsius. All right, this is an example of a moisture effect on decomposition, an F of W multiplier. It's a function from 0 to 1, and on the x-axis is the fraction of soil water saturation. So 0 means there's no water in the soil whatsoever, and a 1 means that the soil pore space is completely saturated. There's no air space whatever left in the soil. And this function just happens to be represented by this power function based on the fraction of saturation, but this is just an example. The main thing to look at is the shape of the curve and understanding what the shape of the curve is telling you. So at about 55% or 0.55 fraction of saturation, this function is its maximum of 1. So that is saying that according to this model, when pore space is about 55% saturated, that would be ideal for the maximum decomposition rate. Anything wetter than that, the microbes have less oxygen and are able to decompose the soil organic matter as effectively. And this fraction of soil water saturation might also be referred to as water-filled pore spaces by some models. Models like the DayCent model don't actually simulate gross primary production and autotrophic respiration separately. They just simulate net primary production. So net primary production, according to the century and DayCent model, is some maximum rate that's plant specific. Some plants grow faster than others, and then multiplied by a temperature function and a moisture function and a solar radiation function. So what's not being considered in this simple model? Well, we're just looking at carbon, but of course plants need nutrients too. So you could have optimal temperature, optimal soil moisture, optimal solar radiation, and your plant may not grow at the maximum rate because there's not enough nitrogen available. So we'll talk about nitrogen cycle a little bit later in these lectures. So we looked at functions of temperature and soil moisture effects on decomposition. Let's look at some on plant production, and they're going to have similar shapes. So here is an example of a temperature curve for a plant. This would be very plant specific. Each plant you represent by a model might have different curves. Some plants might grow better at warmer temperatures, some might grow better at colder temperatures. Some can tolerate heat better than others. So this is just an example. It has a very complex equation. But the thing to look at is it's, again, a 0 to 1 multiplier on which will multiply a maximum rate of plant production. And it's 0 at really cold temperatures, and it's 0 when it gets really hot at 45 Celsius here. But it's at its maximum at 30 degrees Celsius. So for this particular plant, it grows best at 30 degrees C, and anything less than that or anything greater than that, there's no plant growth. And so you could plug in values into this more complex equation so that the optimal temperature of 30 degrees C, T-opt, would be plugged into the T-opt variables in this equation, and the maximum temperature 45 degrees C would be plugged into the Tmax variables in this equation to get this particular curve. And you could change the Tmax and T-opt for different plants. A soil moisture effect on plant production. Again, this is just an example. This is the one that Descent uses. And so it's got two parts to it. When soil water content is less than or equal to field capacity, which is represented up to this 1 here, and then when soil moisture is greater than field capacity all the way up to saturation. So when soil moisture is 0, the plant really doesn't grow. This would be a 0 and it would prevent the plant from growing. But as the soil moisture increases, the plant would grow better up to field capacity, which is often considered ideal for most plants, not all plants, but most plants. And then this particular plant is parameterized so production is reduced when water starts filling up the pore space. So under anaerobic conditions, this plant doesn't grow as well, and you can see a decline in production up to the point of soil water saturated. Not a complete reduction and not a complete 0 for plant growth at saturation, but close to 0. And this is just the equation for the first part of this function, and then this is just, I don't have the equation here for the second part of this function, but it's just a linear function. So what is an ecosystem model? Well, an ecosystem is the interaction between organisms and their environment, so that's what an ecosystem model tends to represent, the interactions between organisms and their environment. And in the case of the models we've been talking about, the organisms we've been talking about are the microbes, and the environment is the soil and the, and the biosphere. In terrestrial ecosystem models, they almost always represent plants and soils, and the cycling of carbon and nutrients between the plants and soils. Not all ecosystem models are terrestrial. I'll show you an example in a second. Terrestrial models often include soil water dynamics. They compute the soil water moisture changes with time depending on rainfall and drainage and evaporation and transpiration. And they can compute stream flow. Some models explicitly represent animal populations, means they might have some number of cows grazing in a pasture, or some number of ungulates or wildebeest grazing in a grassland. In other models, they may just implicitly represent them, so they don't really have some number of grazing animals, for example, but they might just say is that some fraction of grass is removed each day, and that's the way grazing is represented, not necessarily by keeping track of an animal population. An ecosystem also refers to the scale of the model. So ecosystem is somewhere in between population and landscape models. So a population model would be one species. You would be model just one species of plants or animals or some type of organisms. A community model would represent interaction between multiple populations, and an ecosystem model is like maybe considered like a single type of ecosystem, like a grassland or a forest or a agricultural field. When a landscape model might have multiple ecosystems, may have, like looking at the figure to the right, where you might have a mountain ecosystem and a floodplain ecosystem. So it's scale. These are also ecosystem models. The left diagram is some body of water like a reservoir or a lake. The right diagram is an ocean ecosystem model. So they all have organisms, their environment that the organisms grow in, cycling of carbon and nutrients between organisms and their environment. So ecosystem models don't have to be land-based, but the carbon cycling is really important. Carbon cycling is not just important to the atmosphere and terrestrial systems, but carbon cycling in water bodies is also very important to being able to compute the global carbon budget and the global carbon cycling. Ecosystem modeling isn't just pools and fluxes, boxes and arrows. There's other type of models too that I wanted to give you an example. Individual-based models or agent-based models. These are different in that each organism is represented, or each plant is represented as an individual rather than a box of carbon. And these individuals have their own unique characteristics. They interact with other individuals, and large-scale processes emerge from the cumulative interactions of all the individuals. Like, for instance, starling murmurations. I think these are really cool. If you've ever seen a video of a starling flock flying through the air, and it looks like one big amorphous organism that has all these really odd shapes, but really what's happening is that there's a bunch of individuals and they're each doing their own thing. They're interacting with their neighbors, they're flying in the flock, and this big amorphous flock with these cool patterns emerges from all the individual starlings that are flying. A more ecosystem-centric idea is looking at forest succession, and in an individual-based model, one might represent each tree as an individual. And there could be multiple species of trees, each has their own properties, their own requirements for nutrients and light and water. They compete with one another. Some are shaded out, some gain access to light. And what happens over time is maybe you might start with one of the plants as a dominant species, but then the other plant might become more dominant over time. And so by the cumulative effect of all these individuals acting over time, the forest succeeds, so this larger scale pattern emerges. So why are so many ecosystem models designed to simulate carbon dynamics? Well, carbon isn't every living thing. Carbon is common to the pools and the fluxes we study in ecosystem ecology, the plants, the soils, the energy sources, and the respiration fluxes. And also ecosystem models usually simulate nitrogen in addition to carbon, but sometimes also phosphorus and potassium. And in terms of greenhouse gases, carbon and nitrogen are constituents of some of the most abundant greenhouse gases on the Earth. And many greenhouse gases have biological origins. For instance, water vapor, carbon dioxide, methane, and nitrous oxide are the top 4 most abundant greenhouse gases according to this 2015 diagram of US greenhouse gas emissions. And these are all represented in ecosystem models. And carbon and nitrogen pools within ecosystem models are thought of as either being sinks or sources of carbon and nitrogen. So from a greenhouse gas standpoint, it's good for a carbon pool to be a sink. It means an ecosystem carbon pool is a sink, such as in the biomass or soil, then it's keeping it out of the atmosphere or pulling it out of the atmosphere. And the same with nitrogen. Nitrogen is often too abundant in some ecosystems, and so having a sink of nitrogen where nitrogen is stored and doesn't pollute the environment is also a desirable thing from an environmental standpoint. So this is the end of part 1, and I will see you in part 2.